Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're going to look at a previous exam question. This question comes from the 2023 Higher Level paper and it is question 4. A ball of mass mkg is projected with initial velocity 15 meters per second. I'm just going to highlight this because it's something we're going to need later in the question. It's projected with initial velocity 50 meters per second vertically downwards into a tank of water. The ball travels through the water against an upward buoyant force that is 4 times the magnitude of the weight of the ball and a drag force of mv squared newtons. Draw a diagram to show the forces acting on the ball while it is moving downwards through the water. Okay, so here's our ball, and one thing that will always act on any particle we have is weight. So we have our weight, which is mass times gravity. Now we're told that there is an upward buoyant force. So that's not dependent on anything. So buoyant, we're going to use B, and it's 4 times the magnitude of weight, which is going to be 4 mg. So 4 times. Now, the direction we have is downwards in this question. So we're moving down, which means that the drag force is going to move up. So the drag will always go against the motion or against the direction of travel. So we get here our drag force, which we can call D, which is mv squared. Now notice how that initial velocity does not go on our force diagram because it's not a force. You can put it to the side if you like, but really that's just going to be needed later on in the question when we're setting up our differential equation. It's telling us what's initially happening for our velocity, so it is not relevant right now. So the next thing, part 2, what they ask us to do is show that while the ball is moving downwards, the rate of change of its velocity, v, with respect to its distance s, so this is v dv ds, below the surface of the water can be expressed by this differential equation. So v dv ds is just another way to say acceleration. So what we're going to start with, anytime we have a force diagram, we always start with F equals ma. We're moving in a downward direction, meaning mg will be positive. Then we take away anything that's moving upwards, so our buoyant force, and then our drag force, and that is equal to mass times acceleration. The m's can be divided out, giving us minus 3g minus v squared equals a. Now, we're very close to what we were given, so we actually can calculate minus 3 times g, which is minus 3 times 9.8, gives us minus 29.4 minus v squared. And then we know that actually acceleration, there's 2 ways to write it. We can write it as dv dt, which relates velocity to time. But in this case, they want us to relate velocity to displacement. So it's v dv ds. So we get v dv ds equals minus 29.4 minus v squared. And now we have our differential equation. So part 3, solve this differential equation to find an expression for v in terms of s. So it's very nice in this question that part 2 asked us to get the differential equation but gave us what that differential equation should be. So even if we weren't able to get the correct one, or even if we weren't able to do it at all, we still have the differential equation, so we can move on to part 3 to solve it. In the case where you can't work out the differential equation, or in the case where you've worked it out incorrectly, do use the one that they've given you, because if you use an incorrect one, it may not, you may not be able to integrate it. So our first step, once we have the differential equation, is to separate it. What we mean by that is we want to move our variables to each side. So here, what we're going to do, we're going to bring the whole 29.4 and the v squared across. You can do that with the negative. You can leave the negative on the other side. doesn't really matter. So for us, what I'm going to do is I'm going to keep my v dv ds. I'm going to pull out that minus, and I'm going to bring that whole bracket underneath the line on the left hand side. So we have 29.4 plus v squared dv, and then I have a minus ds, and we're going to integrate both sides. Now, S is our displacement. So displacement, unless you're told otherwise, will always start at 0, because we talk about generally how far you've displaced from its starting point. So when displacement was 0, so that was at the very start, the initial velocity, we had this earlier in the question, is going to be 15. And then when the displacement is S, the velocity is V. So on the right hand side, that's going to integrate really, really nicely and quickly. Generally, you're going to get marks integrating both sides. So don't be put off by kind of complicated integration. Make sure you do your simple integration, even if you can't do the left hand side, or if you feel that that's wrong, or if you give up. Still, we have a minus S on that right hand side. Our focus is going to be, so I'm going to just put that in. So that's my minus S, and we're going to evaluate that between 0 and S. Straight away, I've got some marks. Now over here, the left hand side, I'm going to just bring it over here so we have a little bit more space to work. So we have the integral evaluated between 15 and V, 29.4 plus V squared dV. So our focus now is, what do we do with this? So here's our little checklist. First thing we check is there a formula on page 26? Now we have 3 little exceptions that won't look exactly the same, but otherwise it has to be identical. That bottom line does look like something we may be able to use. However, the fact that there's a V in the top line is a little bit, we're not really sure. It's not going to be exactly like something we see on page 26. The next thing is it a composite function? Now, this is a composite function. It can be really hard to see. Effectively, what we have is a 1 over x, but the bottom line has then been made more complicated. I know students really struggle with identifying this, but let me give you kind of how you could make sense of this in an exam. So if you weren't sure if it's a composite function, you could say, right, is it integration by parts? Now, the one key giveaway that this is definitely not integration by parts is the fact that the two parts, yes, we can make this a multiplication, because integration by parts should be a product, should be multiplication. We can create that second piece as a bracket to the power of -1. However, what gives it away that it's definitely not integration by parts is the two pieces are both algebraic. So for our integration by parts, we'll see that the two bits will generally be different. So go back to our inlate, I-N-L-A-T-E, inverse, L for logs, A for algebra, T for trigonometric, and E for exponential. They should be two different pieces. So the fact that these are both algebra implies that it's probably not integration by parts. So that gives us back to our composite function. It is a good idea to really try and make sense of your composite function and try figure it out. If we have a composite function, we're going to use substitution. The substitution, we always sub in for the more complicated piece. So we use U, and I'm going to take the bottom line because that's more complicated than the top line. The top line is just a V. We're not going to go anywhere with that. So we get 29.4 plus V squared, and then we differentiate that, du dx, and that, du dv, and that gives us 2V. And then what we want to do is we want to rearrange this. So we get du is equal to 2phi dv. Now what we're effectively trying to do here is we want to replace this with the du. Now if you look at our question, we have a v dv. We don't actually have the 2. So what we can do is we bring that 2 back over the line as a half. So we have a half du is equal to v dv, and now we can sub that in for the bit in yellow, which means when we get to our integration by substitution, it's going to look something like this. So we have the integral, and we have all over u because we've simplified it, and then we have a half du. So we have something that looks like this. Now that can be cleaned up into 1 over 2u du. Equally, you can pull that half out in front if you want, absolutely fine. And then when we do that integration, we end up with ln of 2u, and then divided by the derivative of the inner function. So again, if you want to think that as a half in front, that's absolutely fine. So when we come back over here to that left-hand side, what we have is a half, the natural log of, instead of 2u, we're going to put back in what we had. So 2 and our u, which was here, make sure you do any substitution back in before you do your evaluating. And then that needs to be evaluated between v and 15. Now, if you pull the half out in front over here, you get a slightly different answer. So you will end up with a half natural log of u, and you might feel, well, that's completely different. However, because of the way we're going to work this through, because of how we evaluated, you will end up with the exact same answer if you pull that half out in front and you've just a half ln u for this part here. So now that we have our integration done, let's do our evaluating. We have a half natural log of 58.8 plus 2v squared. Take away a half natural log 58.8 plus 2, and instead of v we're putting in 15 squared, and that's all going to equal to minus s minus times 0, which effectively all just disappears. So we're left with minus s on this side. So I can pull that half out in front and then just focus on the natural logs. Subtracting our natural logs allows us to simplify using our laws of logs. So we have 58.8 plus 2v squared, 58.8 plus 450, and that's all equal to minus s. Let's get rid of the half. So we get natural log of 58.8 plus 2v squared all over 508.8, and that's going to equal minus 2s. Remember what we're trying to do, we're trying to find an expression for velocity, v. So we're going to take e to the power on both sides to get rid of that natural log, or however you do get rid of your natural logs. So yeah, 58.8 plus 2v squared. At this point, all we're doing is some algebra. So the differential part is really done. Minus 2s, we bring our 508 above the line. Really take care with this because this kind of stuff can go wrong so easily. So really pay attention. Make sure you are not rushing through it. You're not doing anything terribly silly. You don't make mistakes that'll dock you marks when you've done all the hard stuff. So 58.8, we're going to divide that by 2. So we get v squared equals, you can put it all over 2 or just divide across. I'm going to just divide it across to keep it nice and simple, minus 29.4. So then v is equal to square root of 254.4 e to the power minus 2s minus 29.4, and that's meters per second. So part 4, the ball is at its maximum depth d when v equals 0. Calculate d. So the depth, we're really talking about s, its displacement. So what we're going to do is we're going to sub in when v equals 0, and we're going to try and find a value for s. So I have our answer from part 3 here on the board. V is equal to the square root of 254.4 e to the power of minus 2s minus 29.4. However, if we sub in v equals 0 here, we still have a substantial amount of work to do to get s on its own, to isolate it. So another option is, and this is a really good idea anytime you have a follow-on question from solving a differential equation, think about, is there a line in my previous answer that might be better, that might be, I suppose, easier for me to use than our final answer. So here, because we're looking to find a value for S, so the depth, is there a line from part 3 where we had S either isolated or nearly isolated? And the answer is yes. So we did have a line that looked like this. So minus S is equal to minus half the natural log of 58.8 plus 2v squared all over 58.8 plus 450. Now what that does is it allows us to get an answer for S much quicker. So it turns this sum. So all I'm going to do is I'm going to bring that minus across, and we have the natural log of 58.8 plus 2 times 0 squared. So that's just going to disappear. And then we have 508.8 down there at the bottom. So we can do a little bit of cleanup. And all we're doing now is going straight to our calculator. So this becomes a much nicer and easier sum. We're going to put this into our calculator and we get 1.08 meters, which is correct to 2 decimal places. Now it's absolutely fine to use your final answer and sub that in, but it is going to take away a little bit of time. Remember, the exam will be very tight for time, so anywhere you can save time, you want to do that. So this is a great little trick in these differential equation questions to speed yourself up. So we're told that after reaching its maximum depth, the ball changes direction and begins to move upwards through the water. Draw a diagram to show the forces acting on the ball while it's moving upwards through the water. So here's our ball, and again, it doesn't matter what way it's moving, weight will always move or will always work in a downward direction. So weight is mass times gravity. Then we have an upward buoyant force, which they had already told us was always upwards. That's at the very start of the question, which is 4 times the magnitude of weight. So that doesn't change. So that's 4 mg. Now we need to think about, well, what way are we moving? So we're moving upwards through the water, which means this time drag is going to move downwards. Drag always goes against motion. So think of it as a type of resistance. So then this is our drag, which is mv squared. So they want us then, once we have this part done, to write down a differential equation for the rate of change of velocity. It doesn't say with respect to displacement, so we're happy to think of this as just dv dt. And we're going to start with our F equals ma. We always start with the direction of motion, which is why that additional arrow is so important. So we have 4mg minus mg minus mv squared is equal to ma. And we get rid of all these m's. So we have 4g minus g, which is 3g minus v squared is equal to a. So we can rewrite that as dv dt. You can leave that as 3g. But we already know that that is 29.4, and that's minus v squared. So that's our differential equation for when the ball moves upwards through the water.